Ryan's with Idaho Virtual School, and he is here to share with you about their work in applying machine learning to education data. So Ryan, please give him a warm welcome.
Great, thank you. It's fantastic to be here, and I just would love to reiterate how much I've learned from those conversations. My name is Ryan Gravette. I am the Technology Director for Idaho Digital Learning, and you know, a little bit for some of you who don't know about our organization, we're going to keep this nice and short because that's not what's interesting. But you know, when you think of Idaho, you probably think of this guy, right? Potatoes. When we think of Idaho, we think of a different type of sticker, and that is, you know, the lovely environment in which we get to live in every day. Our organization is focused around serving school districts in the state of Idaho, really focused on making sure that students have opportunities through their local school district by providing online options. And our growth has been great over the year. About 1 in every 5 high school students in the state of Idaho now take a class with us each year. But that doesn't mean that we're a really big organization. In terms of funding, our organization is probably about the size of some of your high schools in terms of staffing and in terms of budget each year. But enough about me. One of the things in our organization, one of the things that we like to do is do everything with partnerships. So as you'll see throughout this presentation, we're partnering with different organizations to do this, the local universities, our regional education board, all those types of things is the way that we love to do things. And in fact, there's some of these organizations here. You can see Georgia on here, Georgia back of the room. I know that Wisconsin presented yesterday. Fantastic partners that we love to do these types of things with. So let's talk a little bit about the lessons learned in machine learning that we've had over the past 3 years. And there's 3 things I really want you to get out of this presentation. Number 1, I'd like you to be lightly entertained, so hopefully I'm going to do that. Number 2, I want you to learn about machine learning and what it can mean for your district and how you need to prepare your district. And then number 3, I want you to learn how not to do it. Because when we talk about lessons learned, we're going to be talking a lot about us doing things the wrong way. And at times that's a little bit humorous, at times it's a little bit painful, but hopefully you learn from us about how not to do machine learning, as well as, you know, maybe how you can in the future. So we started out with a noble goal. And I think that if you talk to vendors, you talk to other people, or you talk to a lot of people in your school district, we wanted to know something similar that you wanted to know, and that is, which of our students are going to struggle in our classes? And so it was very noble. Which one of these students are going to struggle in our classes? And we want to know, given the first 2 weeks of data, and we have lots of data. We're an online school. That means everything that a student does is tracked somehow with data. So given these first 2 weeks of data and information about the student, which one of these students are going to struggle in our classes so we can do some interventions early? And had some great conversations at some conferences and said, you know what, I think we can do this. You see, I think we can do this because machine learning is becoming democratized or commercialized, or consumerization of machine learning is happening in the industry right now too. This is a article by the Wharton School of Business. But you know, what used to be quants and really smart programmers is now turning a little bit into drag and drop. This is the Microsoft Azure interface for machine learning. And you literally can drag and drop elements in and do machine learning. It's taking a lot of the heavy requirements and the heavy lift that it was required before with machines and all sorts of networks and things like that, and turning it into a simplification. And this is just the first step, right? This is going to get easier and easier over time. Technology tells us that this stuff doesn't get harder. This stuff is going to get easier and easier over time. So we took a look at that. So we said, you know, we're not machine learning experts, but hey, there's a bunch of grad students over there at Boise State. Let's throw this out to them and say, hey, we want to learn which one of our students are going to fail, and let's get you this data, and let's partner together. And you know, they were very excited about this project, application of something that they have learned, and an opportunity to really do something that a lot of the industry has been looking to do. And so, you know, very little budget, in fact, no budget whatsoever, we started on this endeavor. So the lesson learned that we had first when we went across this process is that we really didn't know what machine learning is. And it's funny because yesterday we saw a picture of the kids with the what looked like electrocution headphones on and wires, and that was the vision of the future for machine learning, right? But I had this comic in my presentation, and it doesn't look so much different of, do we really think that this is what machine learning is? Or do we think that it's, shredding books and putting them in wires into the machines? No, it's not. That isn't machine learning. So I wanted to take a step back and say a little bit of what we learned about machine learning. So you walk away with this, with a base foundation understanding of what machine learning is. So definition here. Machine learning is the semi-automated extraction of knowledge or patterns from data. Thank you, Wikipedia. Let's break that down a little bit into 3 key areas. Number 1, knowledge from data. We're trying to extract knowledge from data. Number 2, this is going to be an automated extraction or a semi-automated extraction. And number 3, semi-automated means that part of it is automated and part of it is not. And that non-automated part of it means that you have to have really smart people helping to make good decisions going into it. So even though it's drag and drop now from Azure, you still have to have a lot of good decisions going into it. And 90% of machine learning, and we learned this a little later on, 90% of machine learning is just getting your data ready. So there are 2 types of machine learning, and when people talk about machine learning, it's divided into 2 areas: supervised machine learning and unsupervised machine learning. So supervised machine learning is focused on prediction. I have a box, and I'm going to pour the marbles out, and I want to predict where these marbles are going to land in this box or that box. The result is known or contained. I know that I have these boxes. It's going to fill box A or box B, and I want to predict whether or not it's going to be in box A or box B or box C, so on and so forth. Here you can see on the screen a picture of different flowers. And if we're going to use machine learning to look at these images and determine from these images what plant that is, then we could use different vectors to define that. One of the vectors might be petal length, one of the vectors might be petal width, and then we would start using statistics to find these items and group them together through kind of yes or no questions. At its basic element, lots and lots of yes and no questions is supervised machine learning. And there's different elements of that, and of course it's much deeper than that, but at its basic element, that's what it is. Unsupervised machine learning is really saying, well, what is the box? Does the box exist? So I'm going to give lots and lots of data, and the machine is going to try to find patterns in that data and raise those patterns in that data up to the top. You're not giving it a box of where you want it to be or what you want it to be. Instead, and it's not predicting something from you. Instead, it's trying to raise to the top patterns that you may not have seen otherwise. It's basically an automated finding of those patterns. And for the most part, you can't constrain the outcomes, right? You don't know what you're going to get. You pour it into the box, and out comes these patterns, and you look at it and you say, that is totally useless. Or what's known to often happen, you pour it into this box and you find stuff that is grouped together, but it may not be grouped together next year because it just found patterns in the data from this year, but not a pattern that's a true pattern to the data set you were looking at. It just happened to be that that year everybody chose Wrigley gum, and next year it was just an anomaly in the data, and not everybody chooses Wrigley gum. So unsupervised learning is still a vast, wide open space of the area of machine learning. And so when you're thinking about machine learning, almost always people are talking about supervised machine learning. And really, when we asked our question of which students are going to fail, we were asking a supervised machine learning process. If you have time, and I don't have time to go through it today, there is a website called r2d3.us. r2d3.us. Easy to remember because it's just one higher than r2d2, right? So r2d3.us. And what this does is it walks through with you understanding how machine learning really works with trying to figure out whether or not apartment complexes are in one geographic area of the United States or another. It's visual, it's fantastic. In a longer session, we would actually walk through this because it helps you understand it great. R2D3.us, not .com. All right. The second lesson learned that we found out was that although these computer scientists are in the education system, they don't understand education. They don't understand educationese. They really don't understand the difference between what a grade book is, what types of assignments there are, what attendance is. I mean, all these things we assume that they knew because they grew up in the education system, and they don't know it. So you really have to sit down and take time with the team that you're going to be working with and start to explain really what education is. More importantly, they didn't even know what was important and what wasn't important. Because machine learning isn't going to give you what's important and not important. You have to provide that. So examples were Blackboard user activity data. There was all sorts of activities that the students were taking, and they were like, well, is this important? Is this important? Well, it's a grade. Of course it's important. Oh, so you have to limit your data set, and that's the other thing that we learned. You can't just have a massive data set that you're working with. They want to limit that data set, and they can't do that without knowing what's important. Lesson number 3, data can be particularly tricky to share when dealing with student information. And this is a duh element, right? We've just gotten done talking with student security and data security, but we're giving a whole bunch of high school students data that they're going to then hold on their personal laptops and do machine learning with. You've got to make sure that you remove PII from that. But we also wanted to be able to take the data that we got back, especially if it said this student is going to fail, and know what student it is. So you remove all the personally identifiable information and you lose some of the value. And so that became a tricky point for us. And what we ended up doing was hashing the user identifiers. So I know security left, but just use bcrypt or some other encryption. Take that personally identifiable information, throw it through a one-way encryption algorithm, give it to them with that one-way encryption algorithm. They can't use it for anything, but when you get the data back, you can figure out who that aligns to. So it's a way that we found over time to make sure that we anonymize that data, but also provided a way for us to identify that user later. Lesson learned number 4, changing relational data into data that can be used by machine learning is challenging. When you take the data that's in a relational format and give it to data scientists, they have to convert that into a data format that these machines can read. And what we learned is that many of these meant vectorization of our data, which means that different algorithms use different ways, but when you're talking about data sets that are small, and we have data sets that are millions and millions of rows big, that's small data. So when you're using small data, you have to vectorize the data. And what that means is that basically all of your data goes into yes and no questions. So what you thought was simple, like the city, if you're going to punch it into machine learning, it is Boise, yes or no. Not this is the city of Boise. So you have one column that is Boise, yes or no. Then in the next column, Nampa, yes or no. And so what was one column in your database now becomes 100 columns in machine learning. So you have to, and now what that means is that you have to, again, prioritize the attributes. What's going to be important? Is the city really important for the topic that we're discussing? Well, is there going to be differences in the city for these students? Maybe so. It's a different environment. Maybe that does help predict whether or not a student's going to be successful in a class. So you have to choose those attributes. These are just some of the examples that we learned that we had problems with. Also, whenever you're dealing with user data entry, you're going to get gaps and errors. And machine learning does not like gaps and errors. You have to have clean data to do machine learning with. In fact, even things like surveys, one student not taking a survey and one student taking a survey, well, that one student that didn't take that survey is a gap in the data. That ends up being an issue for machine learning. You have to have really clean data. So in the end, we did this and we had an 84% accuracy in predicting which students were going to fail in our class. We were ecstatic. The Boise State team was ecstatic. We were predators and we had delivered our data prey. You know, it was like Simba on Pride Rock, whoa, right? And we delivered this to the teachers. It was fantastic. And instead of Simba on Pride Rock, they looked at us like a cat that had brought in a mouse from outside. And if any of you have cats at home that are so proud walking in the door, purring all the way, rubbing against your leg with the mouse still squirming slightly in its mouth, the first thing you say is, "Get that the hell out of here." That is the response that we got from the teachers. Why? We had just been successful. Well, what was the actionability of those results? We didn't think about that. We know Johnny here, he's 85% confidence he's going to fail. Well, the first thing the teacher asks us is, why? Well, it's a little bit of a black box. Machine learning tells you with a good percent accuracy, 85% accuracy, who's going to fail, but not why. Is that really important? Yes, because if you're going to take action or an intervention with the student, you've got to know why they're going to fail. So it was disappointing. We had to take a step back and say, how do we get useful data to our teachers, and why were these students selected? Because apparently just flagging a student that has an 85% chance of failing isn't good enough. In fact, the teachers would say, I can stand at the back of my classroom, probably within the second week of classes, and do the same thing. They're probably going to fail. They're sleeping in the back of the class. They're using data to do the same thing, but do they know what they need to do after it? You see, one of the key problems that we have in analytics and in machine learning is not thinking about what we're going to do with the data that we get. Next thing is know the infrastructure requirements. They did this all on their laptops. If we were going to replicate this, we'd have to set up server environments, all these other type of things. We realized that we didn't have, we're .NET shop, they're using a whole bunch of PHP and Python, and we didn't have the ability to support this long term or to set this up in an environment. Even if we did want to use it, we weren't, the way that it was delivered to us was a laptop package of a whole bunch of different things. It wasn't sustainable. Should have thought about that at the beginning. So, again, what infrastructure is required? So lesson learned is that we really needed a process. It's a fantastic process to think about what you're going to do in machine learning. And this is a workflow that we decided to put in place. You got to define the problem, you got to prepare your data, you got to spot check algorithms to improve results, and then present the results. And so this is just a workflow that we found that is really important when going through this. Our next step, we decided, well, let's use the same computer scientists from Boise State. They graduated now. Let's contract with them, and let's determine what variables are important. Let's determine what this machine learning did. So we did a whole bunch of statistical analysis. The lesson learned is that if you have a computer scientist and you go through statistical analysis, they're not going to use SPSS or tools like that. They're going to write it themselves again. Okay? So we wrote a small version of SPSS to figure out this information. We probably should have just gone to somebody who was great in statistics, and they would have said, oh yeah, SPSS. There you go. So, and then have an action plan for the data and discuss that action plan with the developers before doing that data analysis. Here's the results that we found. We found out that these algorithms, the machine learning was predicting mainly on geography, race, and ethnicity. So with those three items, I could be 85% accurate in telling you who was going to fail our courses. While that pointed a finger at an institutional problem, it did not give us malleable items that we could change. It's pretty hard to change a student's geography. You can't change a student's ethnicity, and nobody's going to change somebody's race or gender. So we had a racist algorithm, basically. So we had to pivot, and we said, you know what? This is not going in the right direction that we want it to. Clearly, let's start taking a look at why these students aren't succeeding in our classes, but this is not giving us actionable data that we can give to the teacher. Caution, teacher, this student is male and comes from this city. That's not going to be helpful again. So we decided, let's try to focus on some malleable features. We partnered with Education Northwest this time, worked with our machine learning expert and some data experts there, and found out some additional information. But before we get to the additional information, lessons learned there. Number one, gaps in data are horrible. If you don't have consistency with your data, you might as well not even use it. Okay, if you miss a couple of days, that may be all right for daily activities, but when you're doing analysis on your data, just a couple of days of gaps means that you pretty much have to throw it out. Number two, gathering data in a useful format is hard because we have multiple systems. Some of you have 50, 60, 70 different systems or applications that your districts use. You've simplified access on one end through single sign-on, but have you simplified data analysis by having them all report to a single repository or a data warehouse? Well, we haven't. So it took us 3 months to gather data from these different disparate systems in a way that was consistent that we could deliver to them.
So you had to do some field mapping so you could...
That's right. I mean, one system uses username in this way. Another system uses username in this way. One that requires it be an email address. Well, we can't send along an email address because an email address is personally identifiable information. All these types of things we had to think through. And it ended up taking one person's time 3 months to gather all the data. And then we did both machine learning and traditional statistics. What were the results? Well, we found out that engagement as measured by any student activity is a high predictor of success. So if you are engaged with your online class, there's a good chance that you're going to be successful in your online class. If you're not logging in, you're not. Fantastic information. That's a duh moment, right? But on the other hand, getting kids into classes by any means possible and just getting them to log in does have a high correlation with them being successful in that class. So students that aren't logging in is a high risk factor. And then also, we found that grouping students into categories like credit recovery, what about our credit recovery students, or what about our advanced students, didn't have as much value without considering those additional variables like their activity. It didn't matter as much that they were a struggling student coming in or an advanced student coming in. What mattered more was some of their behaviors. But again, limited malleable information that we could take away and deliver to our teachers. And so we decided, let's pivot. Let's pivot away from this getting great information to teachers idea. I need some success here for a little bit. I'm tired of being the cat dragging in the mouse. So we moved into what courses will students take next, and we knew what action we were going to take going into this, right? Which is, we're going to email students some course recommendations. So I want you to predict the top 5 classes that students are going to take next, a la Netflix, and then we'll just send out an email and say, hey, here's some information, some recommendations. So we went through, we used our format, we defined our problem, we went through and decided how we were going to present these results. We took into impact what the underlying structure was. We decided to go with a serverless architecture design in Amazon to deliver this information so that we could use our Python programming languages but not have to deal with the Linux stack, which we couldn't support, as well as we could support the .NET stack. So we went with a serverless architecture, and the results looked a little bit like this in architectural design. A little bit of changes here, but we went from basically you put data into Amazon, Amazon transfers that data into Microsoft, Microsoft does our machine learning, spits the data back into Amazon, we pull that out, run a lot of processes on it, and send out the email. Fun for everybody, right? Some lessons learned. Make sure you have a simple uptake and delivery method. We had problems with getting the data cleanly from one system to another system. Integrating 2 clouds like Microsoft's Azure and AWS is not as simple as it sounds, and doing it securely is even more challenging. Within a cloud, they make it easy. Between clouds, not so easy. Having somebody familiar with all your data is beneficial. For the past 3 years, we've worked with one person from Boise State. That graduate now is running a whole bunch of stuff for Amazon in their machine learning. It's great. It's funny that he chooses Azure machine learning over Amazon's, even though he works for Amazon. But having somebody consistent through that time was really important, because going through this process again would be extremely painful. We do this 3 times a year now. And so once every semester, we pull this information, load it into this machine, if you will, and it chugs out those emails on the other end. That's what the email looks like. Congratulations on completing your course, because we only send it to students that have completed a course. Here's a couple of recommended courses. Simple, easy, runs through that process. So armed with a little bit of success, what are our next steps? We want to go back and take a look at improving student learning again with our machine learning. And this time, we've decided that machine learning must focus on actionable results to move from informational to actionable data. And so we took a look at that and said, what is actionable? Identifying students that are struggling, not actionable. How about identifying interventions that are successful for particular students? Matching an intervention to a student at the right time and the right intervention seems like a great idea. Well, we had a problem in that, and that is that our data isn't ready to do that. And likely your data in your districts aren't ready to do that either. You see, we had a problem in that as we go to prepare data, we need to have data from all of our interventions to know whether or not they're successful, to be able to predict which ones are going to be successful and tell you about them. What interventions do you use in your school districts? All kinds of them. Let's talk about a teacher one. How about a teacher making a call home to the student? When is the right time to call a student to intervene with that student and that parent? How do you track that data? Do you track that data? We do, actually. It's in one system. What about assigning an extra assignment or a YouTube video or things like that? Do you track that data? We don't. So we needed to think about that. Or it's in one of 30 different systems that we're utilizing. This is a discovery video. This is a video, this is an object in BrainPop. Well, each one of those have their own data stores, and none of them share along very easily. So how do I gather the data together to make that happen? And so it's been a problem. How do we store data in a way that makes data connections simple, accurate, and secure? And that's really what we've been working on for the past 6 months or so. And we've been sitting down with great people like Georgia, and Georgia and Keith over there has got some brilliant ideas on this, and we've jumped on that bandwagon. And we're saying what we need to do is we need to create an architecture where everybody plays well together. And this is the brainchild of that architecture. It's at a high level right now. There's lots of great discussions going on. Georgia's taking the lead in this and moving it forward. But really, this is a whole bunch of things. I mean, District SIS, that makes sense. And if you look at this whole architecture makes sense. But this is the area that we need to be able to do over here. Our learning analytics without PII, our machine learning. But to be able to set that up, we need to have a learning record store, or a place where everybody dumps what's going on with the learner. So we know all the interventions that are going on across those, so we can suck those in and evaluate what intervention is right for what student and what's being successful in interventions. And so we've pivoted away for a year on our machine learning. We're not doing any machine learning this year. Instead, we're investing all of our time in saying, how can we push forward an architecture design that helps make this possible? And the stuff that Leilani's doing, the stuff that Georgia's doing, all those fit into that picture and start to make that possible. And so we're really excited about working on that and pushing all of our information into a way that makes it much more accessible and valuable.